Okay, so I guess we can start now. So before starting the session, I would like to tell you few things. Just don't hesitate to interrupt me if whatever I'm explaining is not clear to you guys, and also interrupt me when I'm wrong in some calculations. And then welcome you all for the problem solving session. This is the first problem solving session for the course title Principles of Communication Systems, and myself, Saurashis Chatterjee, a PhD student from IIT Kanpur. So today onwards I'll be holding the problem solving session for this course. So my plan is something like that. We are supposed to solve some assignment problems, of course some sample problems that will help you to solve your weekly assignments. So what I plan to do, actually, I will discuss some sample problems, and in each problem there is usually one key concept. So I would like to explain that concept to you all. I know that Professor Aditya Jagannatham did a remarkable job in explaining the different concepts in his course. I will just try to reiterate them again and again while solving the particular problem, so that it the concepts are really clear to you, and that would help you to solve your assignment problems and also in your final exam. I hope this session is going to helpful to all of you. With that, let us begin. So let's move to the first problem of today's session. So that asks the energy of a power signal, and we have four options: 1, 0.5, 0, and infinity. So the answer is supposed to be one of these. Now the answer can be made very easily, but I would like to first introduce, not exactly introduce, just reiterate the point that there are two things, key things. Let me uh, point it out here. So the question, we see there is two part. First of all, it is asking for the energy, and second thing, it is asking for energy of a power signal. So we have two key concept here. One is energy and one is a power signal. So basically when you say a signal, what comes to our mind? It's something like xt, right? Which is a function of time t, and this is a signal. And when you ask about the energy of a signal, energy of a signal, that we are going to denote by E of x, the mathematical expression is given like something like this: integration minus infinity to infinity absolute value of xt whole square dt. So this is about the mathematics, this is about the math part, what we are going to obtain. So let's just uh, think once from an intuitive part of intuitive perspective, that what do we exactly mean by energy of a signal. So let's say I'm giving you a signal like that, a visual representation of it. It's like it's starting somewhere after, this is a axis t, and this is our signal which has a constant amplitude, that is let's call it a, and it goes on up to infinity in time. So can one of you please volunteer here, just without even looking at the mathematics, what is the energy of this particular signal I have drawn here? Any of you? So any of you willing to answer? Fine. Now let me answer this question. So this signal, you can see it goes to infinity, right? So energy of the signal intuitively is how much energy the signal contains, right? So you can see if the signal goes to infinity and it has some finite amplitude a here, we can intuitively say, even without looking at the mathematical expression, the energy content in the signal is infinite, because the signal itself goes up to infinite time. And when we comes to the maths part, it actually bolsters this argument, because you can see in the expression here, in place of xt we can just replace a, because a doesn't really depends on t, it's a finite value, and at every t like t1 t2 the signal takes value a. So it's like a square dt, integral is minus infinity to infinity. So of course the result is going to be infinity. So by the way, I would like to tell here, when the energy of a signal is infinity, that is not a energy signal. Okay, okay, maybe we can come to the concept of energy signal later, but this is what we have when we say energy of a signal. Now it is asking for a energy of a particular kind of signal, what they are calling as power signal. So we understand this is signal, this one is here signal, but it is not asked, the question doesn't ask for energy of any signal, question asks for energy of a particular kind of signal, which is called power signal. So what do we mean by power signal exactly? So let me give the definition to you first, that power signal is signals whose power is finite. Now the moment I say that signal whose power is finite, the immediate question comes into mind, that how do we compute the power? What do I even mean by that? I have computed the energy of the signal given the expression here. Now what do we mean by power of a signal? So intuitively we can, I will give the expression later, I would rather rely on intuition here, what is mean by power. So let's say power of a signal is a ratio, I would call it, and ratio of what? Energy of the signal in a window of size t, and we are normalizing this energy by dividing it with t. And not only that, now the question comes to the mind, that what should be the size t here. Like, I give the expression power of this signal, fine, which is energy of a signal in a window of size t divided by t, but t is actually this, maybe you can consider t1 up to t2, this is I am calling as window of size t. So what size t should I consider to get the power of a signal? It turns out the power of a signal is defined as when t tends to infinity. So with this in mind, we have already the energy of the signal in a window of size t, we have the expression for here, and let's try to write the power of the signal here. So power is given as follows: limit t tends to infinite minus t by 2 to integral over t by 2. Remember, when we compute the energy, we compute over the whole range, that is minus infinity to infinity, we consider the entire range. But here remember, in the definition of power of a signal, I have already mentioned we are considering the energy of a signal in a window of size t. Now that window is covered here. We are considering not minus infinity to infinity, we are considering minus t by 2 to t by 2. Therefore the window is of size t, and I am willing to compute the energy of signal in this particular window. So this is what energy of the signal in a window of size t is, and this should be divided by t. And when we take the ratio for when t tends to infinity, that is what I call the power of a signal. So this is the expression for power of a signal here. And so power signal, we have already defined that power signal are those signal whose power is finite. So what, let me take a new slide here and reiterate the point. So we have on one hand we have one conclusion here, that power signal is something whose power is finite, and then we obtain the mathematical expression for that p of x as limit t tends to infinite minus t by 2 up to t by 2 absolute value of xt square dt divided by t. So this is the expression of power, and we are claiming the question asks for the power signal where the power is finite. So what should be the energy of power signal? Energy of power signal, E of x, is given as px limit t tends to infinity px times t, because you can see if we bring this t to that side and compute the integral from minus infinity to infinity, what we left with basically here is energy of x. So energy of x is given as limit t tends to infinity px times t. And watch very carefully, when we are concerned with power signal, but this px is finite. And what is the value of t? T tends to infinity. So we are multiplying a finite term with a infinite value. So what is the energy of x going to be of a power signal? X is a power signal here. That is why is px is finite. So some constant times t, where t tends to infinity. Therefore energy comes out to be infinity for a power signal. So our answer here is going to be infinity. So any power signal, that is the power of a signal is finite, its energy is always going to be infinity. That is the key takeaway from this question. And actually this power of a signal expression, it's a bit of complicated thing, that the window size need to be t. Actually that is one kind of signal for which it becomes simplified, and I would like to introduce that signal here because it is kind of pillar of this course and we are going to use it again and again and again. It's called periodic signal. So let me introduce that. So another kind of signal, I would say rather a subclass of signal. Signal is a more generic term. So we call a signal periodic signal when it satisfies this equation here. So when you see this equation, this simple equation, what does it exactly mean? That xt plus capital T is equal to xt. This is the mathematical expression for periodic signal, and that need to be holds for all t, and it should be some k here. K is some integer. I mean it can be positive, negative, like plus 1 2 3 or minus 1 to 3 onwards. It can be any integer. So periodic signal satisfies this equation. So what does exactly comes out from this mathematical? So simply when I say that xt repeats itself over a period of t. So what does I exactly mean by that? The signal has a period t, and after that xt repeats itself. So the simplest example would be something like this. You consider a sine function. I would give the expression of sine function later, but first I would like to draw it. So you consider this kind of a function, right? And see and it goes on like this. So one thing you will observe here, that this point to this point, that is from 0 to this point, this function. Yes, someone have any question? Okay. So we are discussing that you can see in this interval here from 0 up to this, the signal is unique, right? There is no repetition. But you see after this point here, the signal is again just repeating itself, the whatever is there in the previous period of, let's say this is a t, this is a duration t, and this repetition happens until this point. So this is as if it's a copy of the signal from the previous period, this one. And again we can see from this point onwards it again repeats itself. So that is what periodic signals looks like. So when you say that xt is a periodic signal with period t, that basically means the signal repeats itself after, like repeats itself every t period. So within any period of with the t, the signal is unique, but just outside that there is no uniqueness. The signal is just repeating itself again and again, and this should go on for example if you and this is okay, this is called this t here is called as fundamental period. So intuitively you can have one key takeaway here, that periodic signals are actually nice from this point of view. If you observe the signal over a single period, you know all about it, right? Because all the information about the periodic signal is contained within this particular period only. When I mention information, it means the uniqueness, right? So basically what I mean, if there is a periodic signal I know which have a period of t, and I am observing it, I need to observe it over a period of t only. It's kind of taking a snapshot over a period t, this snapshot here, or you can take this snapshot here, it doesn't really matter. You have to just observe it over a period t, and then you will know all about it. Why I am saying all about it? Because then onwards the signal is just repeating itself again and again, so it doesn't really matter. We need to observe it over this period t, and all information about it is hidden there. So this periodic signal occurs in signal and systems, and you will see there are a lot of theories are based on the periodic signal only, but I would just like to point out the power when it comes to compute the power of periodic signal. It comes out actually very nicely. So let me write down the generic definition of power here, that is px is equal to limit t tends to infinite integral minus t by 2 up to t by 2 x t square dt divided by t. So this definition holds for when t tends to infinity. Now I will say that periodic signal, this t window of size t, this is a t sized window, right? T sized window. Okay, let's call it t dash here, because I would like to call t as the fundamental period of this periodic signal, so let it be t dash. So t dash sized window, we basically need to compute the energy over, and this t dash sized window, I am saying this can be written as m times t, right? But t is the fundamental period of the signal, and m is some constant where m tends to infinity. So then when m tends to infinity, t dash is equal to m dash of t, right? So let me introduce a new slide here. So what we have now, we have this px, which is definition for more generic class of signal, that t dash tends to infinity minus t dash by 2 here x t square dt divided over t dash. Now I am saying for periodic signal, we can write t dash as m times t. This is limit when m, okay, let me write it with less clutter here. So limit m tends to infinity, m is some integer, m times t, but t is the fundamental period of x. Now I just replace t dash is equal to mt in this expression here. So what it will be, limit m t tends to infinity, integration now runs from minus mt divided by 2, here mt divided by 2 xt square dt t dash. Now you can see this integral over the absolute value square of xt for inter window of minus mt by 2 to mt, right? But here we are going to use the nice property of periodic signal, which says that xt is identical in every t sized interval. So we are going to use this crucial property of xt here, that xt is identical in every t-sized interval. So when that happens, that means this integral over minus m by mt by 2 to mt by 2, this integral can be written as follows. We can take m outside, minus t by 2 to t by 2 xt absolute value square dt, and t dash also write mt. Now you see the crucial part, this to this can only be written when xt is identical in every t-sized interval, and that is what exactly happens for any periodic signal. So now this m here cancels out. So for a periodic signal, what we are left with, the expression of power is as follows. So this one is here is power of periodic signal. So the good thing is, for any general signal which is not periodic, you have to compute the power of xt over this interval t dash minus t dash by 2 up to t dash by 2. When t dash goes to infinity, basically you have to compute the integral over a very large interval to get the power of the signal. But in periodic signal, only thing you have to do, you need to compute the integral over one period, that is t-sized interval. Here I am writing as minus t by 2 to t by 2 as a symmetry, but let me clarify here, this here can be any t-sized interval. So periodic signal, the computation of power is extremely easy. You need not wait, we need not compute the integral over the very large time interval, very large window here. You need to compute the interval only over a period, and you have to normalize that with the fundamental period. You will obtain the power of the periodic signal. So I emphasize the part of periodic signal here because in a few of the next problems we are anyway going to encounter the periodic signal again and again and throughout the course, so it's a good point to introduce it, like what are the benefits we are get from periodic signal. So any question till this point? Okay, then we can let's move to the next question. So here the question is a bit uh, similar kind only. It just say what is the power of an energy signal. Fine. So here are also two things. We are supposed to compute the power, and we are not supposed to compute the power of any signal, we are supposed to compute the power of a energy signal. So when we call energy signal, what does it mean? It simply means signal with finite energy. That is the simple thing. Energy signals are those signals which have finite energy. So if we write the expression of energy here, Ex minus infinity to infinity absolute value square of xt, integral of that, this is finite. This is what all they mean by energy signal. Now we have to compute the power of this energy signal. So let's write the generic expression of power px, which is limit t tends to infinity minus t by 2 to t by 2 absolute value square of xt dt over t. So remember, this is power in t sized window. This is what power is. So this should be less than minus infinity to infinity absolute value of xt square dt over t, where limit t tends to 0. I hope I am able to make you understand why I use this inequality. This term is less than equal to this term, and why I say that, you can see this is the integral over a window of size t minus t by 2 to t by 2, and here the integral over the entire range, that is minus infinity to infinity. And since the integrand here is absolute value square, it's positive, so therefore if you integrate a positive uh, quantity over the entire range, it should act as a always upper bound over any smaller range. So when I say t sized window, it's a subset of minus infinity to infinity. So let me emphasize here, when I call t sized window, that is minus t by 2 to t by 2 is a subset of minus infinity to infinity. And since we are integrating a absolute value square, which is a positive quantity, the integral of this over the entire range minus infinity to infinity is always greater than the energy, always greater than the integral over a t sized window. Intuitively we can say that energy in a t sized window is always equal to or less than the energy of the signal in its entirety. So this is what we get. So, and what is this expression here? This is nothing but the energy of signal Ex. So we get the energy of Px is Ex less than equal to Ex divided by t, where limit t tends to infinity. And I am computing this for, remember, energy signal. So this Ex here is finite. Now can one of you tell me what I am going to get here? I have a finite quantity here, Ex divided by t, where t tends to infinity. So what is supposed to be the ratio here? Any of you willing to volunteer? Yes, right. Sorry, I didn't exactly hear you. Can you just repeat yourself once? Kaushalya said it is 0. Kavi also said it's 0. Correct. It is going to be 0 because it's a finite term, some constant, and divided by infinity, so it basically turns out to be 0. So what we find for energy signal, we have Px less than equal to 0, but power is a always non-negative quantity, so it should be greater than equal to 0, because it's energy. If you go to this expression here, generic expression of power, what I have written, okay, here the expression of Px, since it's this term is always non-negative, so this Px, okay, the pen is not working, just a moment. It's working now. So when when we have written the generic expression of power, this Px is always greater than equal to 0. Why? Because the numerator here is the energy over a t-sized window, and energy is always going to be non-negative. That we can see from the expression of here only. Since the integrand itself is a positive value, no matter what point you choose to integrate over with, the energy is always going to be a non-negative quantity. So from the generic expression of power we obtain Px greater than equal to 0, that is going to uh, this is kind of universal. So just let me okay, so Px greater than 0 we already have. This is universal. This doesn't depends on any particular kind of signal. It is true for all kind of signal. And for this energy signal, we obtained this is 2, and this we denote as 1. So this is true for all kind of signal, and just for energy signal we obtain this second inequality, which says that Px less than equal to 0. So what is the value that is going to satisfy them both? Px less than equal to 0 also need to be satisfied, and Px greater than equal to 0 need to be satisfied. You can see the only option we are left with is Px is equal to 0. So that is going to satisfy both these equations. Remember, this one comes from the universal definition of power, that it's going to be non-negative always. And for energy signal, we did make the computation here, and we reached the conclusion that it is less than equal to 0. So we have to satisfy both of them in order to get our answer. So that comes out to be 0. So power of energy signal is always 0. So here I tried to cover both the concept of energy and power signal as they are in the week 1 lecture. So if there is no question till this point, we can move to the next problem. Okay, fine, let us move to our next problem. So next problem is concerned with the Fourier transform of some signals, different kind of signals, continuous time periodic signals and continuous time aperiodic signal. So before answering that question, let us see what happens. Fourier transform is I would like to discuss first Fourier series here, because and then I would extend the idea to Fourier transform. How we can connect them, we'll see then. So let us talk about Fourier series here first. This I am doing because from the idea of Fourier series only I will try to derive the concept of Fourier transform. So let's talk about Fourier series. So what is this Fourier series and Fourier transform? So let me write in short. Fourier series and Fourier transform are concerned with frequency domain representation okay, so frequency domain representation of signal. So this Fourier series and Fourier transform, basically they are concerned with the frequency domain representation of the signal. So why do we really care about them? So let's talk about Fourier series first. So Fourier series is only defined for periodic signals. So Fourier series is only defined for periodic signals. Why is that? Let's consider the simplest of them, xt, a periodic signal being sine 2 pi f t, right? And if I would like to draw its graph here, so we'll obtain something like this. So let's try to find its period here. What is the period? So according to the formula, x t should be equal to x t plus uh, some integer k times t, but t is supposed to be the fundamental period of the signal. So according to the formula, if we compute sine 2 pi f t plus kt, what we are going to see is sine 2 pi f t plus 2 pi f k t, right? And we'll have sine 2 pi f t plus 2 pi k f t. So when f is equal to 1 by t or ft is equal to 1, what we obtain? F is equal to 1 by t, we are going to see it's just sine 2 pi ft plus 2 pi k, right? And what is that going to be? It's sine 2 pi ft again, because it's just integer multiple of 2 pi, whether it's minus or plus, it doesn't really matter. You will get sine 2 pi ft. And when this will happen, f is fundamental frequency, and the inverse of that is fundamental period. So idea is that this signal here has frequency f. So what does the Fourier series? Let's write the mathematical expression of Fourier series first. So it allows you to represent the signal x here in the frequency domain. And how is so? So it's like k is equal to minus infinity to infinity ck e to the power j 2 pi f, sorry, 2 pi kft here. 2 pi kft. So you notice one thing, this one here is something called, this is complex sinusoid. So you see, this is the Fourier series expression, xt is equal to ck times e to the power j 2 pi kft is the Fourier series expression, and these are the Fourier series coefficient ck. Now what does this k actually represent? So let me go to the next page here. So xt is equal to k from minus infinity to infinity ck e to the power j 2 pi kft. So this is what is Fourier series representation. Now where the frequency domain representation or the spectrum here coming into picture. So as of now we have seen that xt is a periodic signal with fundamental frequency f and fundamental period t, where the fundamental frequency and fundamental period have this inverse relation. So this we know that xt is a periodic signal with fundamental frequency f. Till that point we are fine. But what do we mean by the frequency domain representation? So actually Fourier series allow you, Fourier series you can say, first of all you observe this, Fourier series is not defined for every frequency here, right? You focus on this kf terms. So kf corresponds to kth harmonic. You see that f is the frequency of this periodic signal, and Fourier series is not a continuous function of frequency. It is only defined at the multiples of fundamental frequency. So that's the first key takeaway here. So Fourier series, first key takeaway here is it is discrete in frequency and only defined at integer multiples of fundamental frequency f. So xt is a periodic signal with fundamental frequency f. The Fourier series representation only defined for integer multiple of this fundamental frequency f, which are called harmonics, like kf is the kth harmonic, and corresponding to that you have this non-zero coefficients. So if I try to plot xt in the frequency domain here, frequency domain, let me say in terms of omega. So we can see here that there is this point here, this point here, this here, this, and something here also. So you can see this is at f, this is at 0, this is at minus f, this is at 2f, this is at 2f, sorry, minus 2f, this is at minus 3f, this one is at minus 3f. So this corresponds to c0 here, this is c1, this is c2, this is c3, this is c minus 1, this is c minus 2, this is c minus 3. So you can see the relation between them. So xt is a periodic signal as of now is seen as a function of time, but we say xt is a periodic signal with fundamental period t. That means fundamental period and fundamental frequency are always connected. Whenever you say it's periodic with fundamental period t, that means its fundamental frequency is 1 over t, that we denote as f. Now if we go for the frequency domain representation, we need Fourier series. Fourier series is only applicable when you are going for frequency domain representation of periodic signals. So what we obtain from the Fourier series, we see that it's discrete in frequency. First of all, it is not defined at all frequencies. It is only defined at the integer multiple of the fundamental frequency, which we call the harmonics. And not only that, we have different coefficients ck associated with each of them. So it's like Fourier series. Someone is asking any questions? You can. Okay, fine. So the second thing is Fourier series allows us to write the signal as summation of signal parts at different harmonics of fundamental frequency. So you see, Fourier series is closely related to the fundamental frequency of the signal. First of all, it's only defined for the integer multiple of the fundamental frequency, and it allows you to write this xt, this is the whole signal, as summation of its signal parts at different harmonics of fundamental frequency. Now when I say this term, the signal parts at different harmonics of fundamental frequency, these are actually called spectral uh, informations we can call. So xt, usually what it happens for a periodic signal, it has non-zero coefficients not only at the fundamental frequency but also at the harmonics of them. But usually these harmonics power are less stronger compared to the fundamental one, but they remains. So xt can be written as summation of its spectral, say information is not an accurate term, so it should be components is a much closer. So spectral components. So basically this allows us to see xt, like what constitute xt. Earlier we have just xt, which is a function, like a function of a t time. The moment we go for its frequency domain representation, is actually shows xt as a summation of different spectral components. So actually we can see that at what frequency xt has some non-zero value that corresponds to strength. We'll come to that a few problems later when we will discuss Parseval theorem, which allows actually to express the power of xt in terms of this absolute value of this c case, that is the spectral components. So frequency domain representation is immensely useful because it reveals to you the spectral component of xt. You get to know what frequency is contained in xt, and usually it's not only in the fundamental frequency, the some amount of power, no matter how less they are, also remains at harmonic of these frequencies also. So that is what about Fourier series. But remember, Fourier series is only defined for periodic signal. Now what happens, okay, let me introduce a new slide here, because the earlier question was regarding the Fourier transform. So why we need Fourier transform at first place? So let me say a few words on that. So you see, Fourier series is only defined for periodic signals, right? Let me re-emphasize the point. Fourier series is only defined for periodic signals, right? So what about aperiodic signal? So they also reserve some frequency domain representation, right? It's not only that periodic signals only have this. So what happens actually, if you try to define aperiodic signals in terms of periodic, maybe we can get an idea of what Fourier transform can be. So let's say I am making this statement first, that aperiodic signal are also periodic with fundamental period t is equal to infinite. So I am making this statement. So do you people agree? So basically periodic signal is a signal which repeats itself over after every t interval. And aperiodic signals which don't repeat themselves at all, those are actually aperiodic signal. So to bring aperiodic signal within the framework of periodic signal, I am making the statement that aperiodic signals are also periodic with fundamental period t is equal to infinity. So basically my claim is that aperiodic signals also repeat themselves, but only after a infinite interval. So in practice they basically don't repeat themselves at all, right? So that is how I try to balance the both definition. So in practice t is equal to infinite is not going to be achieved, so the signal is aperiodic, it means it don't repeat itself. But to make it fall under the periodic signal framework, I am saying that they are periodic with fundamental period t is equal to infinity. So that statement I can make. So then we can bring the aperiodic signal also in the periodic signal framework. But the problem is that whenever you say that your fundamental period t is equal to infinite, what happened to your fundamental frequency? Fundamental frequency. Your fundamental frequency f, that is we have already established earlier, is nothing but the 1 over t is tends to 0 for t tends to infinity, right? Now for every aperiodic signal your fundamental frequency tends to 0. Now compare with the periodic signal case. In that case you have Fourier series, right? You have spectral coefficients at different at integer harmonics of fundamental frequency. So let's try to bring the idea here also. So frequency domain representation will have spectral components at 0 plus minus f plus minus 2f plus minus 3f onwards, right? But what if f tends to very 0, like very minute? So consider this plot I have drawn here for a periodic signal. Okay, this plot here. So what I say that f is very small, so therefore the gap between f and 2f are going to be very small, right? So this gap basically just a moment, my screen freezed. Okay, yeah, it's available. So let me just draw here only two components, that is one at f and another is at 2f. But for aperiodic signal what is happening, your t tends to infinity, your f tends to 0, therefore the gap between f and 2f, this is very small, right? This is almost tends to 0. So you are supposed to have spectral components at 0 plus minus a plus minus 2a plus minus 3f. What happens when this f tends to 0? That means you have almost spectral components at every frequency, right? Now remember Fourier series were defined at discrete frequencies only. It doesn't allow the have any spectral component here. It is only defined at the integer harmonics of your fundamental frequency. But what if for aperiodic signal the fundamental frequency itself comes out to be 0? Then your spectral components are going to be same only, like 0 plus minus a plus minus 2f, but there will be virtually no gap between them. So for aperiodic signal we can see, let me write it down here. For aperiodic signal, first of all, frequency domain representation become continuous. It doesn't remain discrete anymore, right? Because there is infinitesimal gap between plus f and plus 2f. It's only a gap of f, which itself goes to 0. That means the representation is no more discrete. The representation comes like you can see here, the representation, this gap reduces, and at a point there is virtually no difference between them. So now they are, for aperiodic signal, the frequency domain representation doesn't remain discrete in frequency as observed for periodic signal. Now it becomes continuous. So that is where the concept of Fourier series starts to fall out. So now let me point down one thing, that now summation what you have in Fourier series, if you go here the Fourier series expression, you have summation over spectral components at integer harmonics of fundamental frequency. Now for aperiodic signal, what is happening, or summation tends to integration. Why is that? Because summation is valid when you have discrete function, but when this gap between the discrete points become infinitesimally small, your function become continuous. So the frequency domain representation aperiodic signal became continuous. Now the summation will become integration. I think now I am making sense why I defined the Fourier series first, because the concept of periodic signal and the frequency domain representation of that, which is the Fourier series, are easier to understand at the beginning. But now once that is established, I am extending the definition for aperiodic signal by claiming aperiodic signals have fundamental period infinite, and from the argument then we bring that into the framework of periodic signal. We have our spectral components as plus minus f plus minus 2f, but now the f itself tends to infinity. Therefore for aperiodic signal, frequency domain representation is actually continuous. So the Fourier series, you have summation because your function is defined at discrete frequencies, but for aperiodic signal it will now become integration, which become a continuous function of the frequency f. And now I will give the Fourier transform, which is defined as xf for a aperiodic signal xt is given as xt e to the power minus j 2 pi ft dt minus infinity to infinity. So this is what Fourier transform is for, and it is defined for aperiodic signal. So I hope this point I am able to make you understand. If you have any query regarding that, you can ask me. So you have any questions or doubts the way I tried to explain Fourier series first, then I extend the definition to Fourier transform? So I would like to emphasize on this point again, that in Fourier series we have spectral components at different frequencies. Now for aperiodic signal, since your fundamental frequency itself goes to 0, now it becomes the frequency domain representation becomes continuous in frequency, and that is why you need to introduce something called Fourier transform to have a valid frequency domain representation for aperiodic signals. So to answer the question here, what what was the original question? So original question was the Fourier transform can be found for continuous time aperiodic signal. So with that, let us move to our third question, that says that trigonometric series representation of a periodic signal xt with fundamental frequency f naught is given as follows. We need to find the coefficient of an for n not tends to 0, and what should be is given as. Okay, so we have given four options, 1 2 3 4. So we have to find the coefficient an, and which one of this is the correct answer. So let us begin with this one first, the second, to see what will happen. So we have 2 f naught. Let's sideline the constant part as of now. Let's focus on computing the integral. So the integral is defined from minus 1 over 2 f naught 1 over 2 f naught. By the way, you can see here this is nothing but t by 2 and minus t by 2. So the integration is over a period. By the way, you can see here it's a fundamental frequency is f naught, so your fundamental period is t, which is just 1 over f naught, and since the integral is happening basically over one period, so we have xt cos, sorry, I will start with second, let's say sine 2 pi n f naught t dt. So let me expand xt here. So what we'll have, minus 1 over 2 f naught, here I have 1 over 2 f naught, then I have a naught plus integral of n is equal to 1 to infinite a n cos 2 pi n f naught t sine 2 pi n f naught t plus n is equal to 1 to infinity bn sine square 2 pi n f naught t, and then we have dt. So let us separate the terms one by one. Integration limits I am not writing again and again, just let it be as a, okay, here it should be a naught times sine 2 pi n f naught t. So here we have a naught sine 2 pi n f naught t dt, plus we can interchange the order of summation and integral here. This will come here and this will come inside. So we have summation n is equal to 1 up to infinite a n is a constant, and what is the this cos a sin a, so it would be nothing but 1 over 2 sine 4 pi n f naught t integration dt, and again we have plus sum over n is equal to 1 up to infinite, this is sine square, it can be written as 1 over 2, let me write it down here, bn by 2 1 minus cos 4 pi f naught n t dt. So we are supposed to find a n from this expression. but the only way the an is contained in the expression is here. So let us bring out that and let's see whether we can get an from here or not. So here the term containing an is given as follows: an over 2 minus t by 2 to t by 2 sine 4 pi n f naught t dt. So you can see this is a periodic signal, this is a periodic signal with fundamental frequency n times f naught. So that means its fundamental period is t over n, and whenever we uh, integrate a periodic signal like this over one period, this will get us 0, because this is not for all periodic signal, this is for this kind of sinusoid signal. And let me explain the reason here in a nutshell why this will happen. So let's consider the signal here sine 2 pi f naught t. Okay, so this is a periodic with just a minute. Okay, it's periodic with fundamental frequency f naught, right? So this function I am drawing only on the positive axis, so we are interested about this integral here. So this is actually 0 here, and this is period, so we are considering the integral over one period. So this is also can be said as 1 over f, and this here is 1 over 2f. So we can see so we have to we are computing sine of 2 pi f naught of t from 1 over 2 and compute it from this integral can be from 0 to 1 over f, and this integral can also be over minus 1 over 2f to 1 over 2f. It doesn't matter, because for periodic signal we already established the the integration limits does not matter as long as the integration interval remain of size 1 over f naught, or just t. So we are basically integrating this periodic signal with period f naught, we are integrating over a one period. So what will happen, basically you can see for a sinusoid, so if you compute these values at this particular location, these arrows, so in one period any sinusoid will have positive cycle and negative cycles, right? So what will happen when you integrate this sinusoid over one period? What is going to happen? This one here and this one here cancel each other out, positive value, negative value. Similarly this here and this here, they also cancel each other out. Similarly, for every value corresponds to this positive quadrant, there will be something of a same magnitude, but the direction is different, that is negative, of similar magnitude will be present in the negative quadrant. So when you basically integrate over one full interval, sorry, one full period, your positive quadrant and your negative quadrant effectively cancels each other. So therefore this integral here goes to 0, and it doesn't really matter whether you are integrating it over 0 to 1 over f or minus 1 over 2f to 1 over 2f, as long as your integration period is t or 1 over f, this integral is always going to be 0. And this is because of this reason: for every value in the positive quadrant there will be something in negative quadrant that cancel it, so that overall result, overall integral should produce you 0. So let me point it out here: sinusoid signal, okay, integration of sinusoid signal with period, let's say frequency here, frequency f naught over any 1 over f naught sized interval will produce 0. And here what we are doing here, you can see this is a periodic signal with fundamental frequency n f naught. So basically the integration is over uh, n number of fundamental period. So its fundamental period is t over n, which is denoted as t dash, and the integral is t. So it's basically you are integrating it over n number of such periods. So of course this is going to be 0, so there is no way for you to recover n from this. So second is at least not going to be the answer. So let us check with the first one what will happen. So in the first case we have the follows: in first case we have integration over same xt cos 2 pi f naught t. Okay, so in the first case we have integration xt cos 2 pi n f naught t dt. So we expand it as a naught cos 2 pi n f naught t dt. Integration range is minus 2 f naught to 1 over 2 f naught plus n is equal to 1 up to infinite minus 1 over 2 f naught to 1 over 2 f naught a n cos square 2 pi n f naught t dt plus n is equal to 1 infinite minus 1 over 2 f naught 1 over 2 f naught bn bn over 2, it will become sine 4 pi n f naught t dt. So you can see all the integral here is basically turn out to be integrating a sinusoid of frequency n f naught over a period f naught. So this is going to be basically goes to 0, this goes to 0 here. So let me point them. So this goes to 0, this here also goes to 0. Now let's see what happens here. We are willing to find an, right? So okay, I think there is one mismatch here. I should not say it n here, let's call it n dash. So it is more like cos 2 pi n f naught t. So that should be cos um, 2 pi n dash f naught t dt. So these two anyway are going to be 0. Now this one here we have corresponds to an. We'll have an minus 1 over 2 f naught to 1 over 2 f naught an cos square 2 pi uh, n f naught t dt plus n dash not equal to n a n dash, this should be n dash here, integration cos 2 pi n dash f naught t cos 2 pi n f naught t dt. Now this here you can see it would result into two integrals, that is cos 2 pi, one is n dash plus n f naught and another is cos 2 pi n dash minus n f naught t. So these are two sinusoids, one with frequency n dash plus n and n dash minus n f naught. These are basically non-zero, so are integer so they have frequency fundamental frequency n dash plus n times f naught and n dash minus n times f naught, and their integral over a period of f naught are always going to be 0. So this term also goes to 0 for all n dash not equal to n. So we are basically left with this one, and it's a and cos square we can write it as uh, so this integral I am just considering without an. Okay, we can bring an here, integral minus 1 over 2 f naught to 1 over 2 f naught here. We have a cos of 4 pi n f naught t minus 1 over 2 dt. And in there is some, I guess, okay, there is this f naught constant part out there. So we have an times f naught. Again this is a sinusoid with frequency 2 n f naught, so its integral over this period is going to be 0. So only thing we are left with is minus 1 by 2 and the integral limit basically 1 over 2 f naught. So we are left with this answer minus n by 2. Okay, did I make some mistake here? Okay, I think I have misread the answer here. The correct answer should be 2 f naught here and minus, so minus 2 must be multiplied. In that case only we'll have minus 2 1 and you'll obtain an here. Okay, so this is the correct answer, and there is actually a good way we can find here. If you talk about the Fourier series expansion of a periodic signal xt, which is given as let's say we have seen earlier k runs from minus infinity to infinity, ck e to the power j 2 pi f naught t. So this we have seen already, the Fourier series expansion of a signal with fundamental frequency f naught. So we have spectral components at integer harmonics of fundamental frequency f. So this problem earlier we have discussed as striking similarity, because if you want to find the value of ck here, what we need to do, we have to integrate the signal xt here with the complex sinusoid corresponds to the kth coefficient. Okay, it should be k here. So here we should have e to the power minus j 2 pi k f naught t. So we have to multiply xt with the corresponding, um, suppose we are willing to find the kth spectral coefficient, then we have to multiply the complex sinusoid with frequency kth harmonics of the fundamental frequency, uh, conjugate of that, and take integral over the period of t. So that is how you are going to obtain ck. Actually, if you do the calculation here, you can see here 1 over t minus t by 2 to t by 2. You can expand xt here. You will have k is equal to minus infinity to infinity here, and you will have ck e to the power, okay, this I should make k dash here, ck dash e to the power um, minus j 2 pi um, k minus k dash f naught t dt. Did I write it correct? Yeah, it's correct only. Now I'll next bring the integral inside and summation outside. So what will basically left with minus t by 2 to t by 2. Let's take out the kth term, that is ck, where this k minus k dash is going to be 0. Then we are basically left with ck dt plus 1 over t integral minus t by 2 to t by 2 ck dash e to the power minus j 2 pi. K minus k dash is non-zero here, so let us denote with something called k tilde f naught t dt. So this is a complex sinusoid with the fundamental frequency uh, k tilde f naught, and we are basically integrating them over one period. So what we will end up getting is 0. Actually you can integrate and check yourself. It will basically result into minus j 2 pi k tilde f naught, and inside you will have e to the power minus j 2 pi k tilde minus e to the power minus j 2 pi k tilde positive, and okay, sorry, it should not be there should not be 2 here, it will only pi k, right? 2 pi k f naught t over 2, yes. And you can see the phase difference between them, phase difference between two sinusoids here is pi k minus pi. So it's the phase difference basically 2 pi k tilde, where k tilde is some integer, and whenever the phase difference is some integer multiple of 2 pi, this term essentially going to 0. So this all terms will cancel out each other, so we are remaining with only this term, and this term ck is a constant, you just take it outside. So we have ck 1 over t integral of dt from this interval, so that will produce t again, so you will obtain ck. So that is how you recover the kth spectral coefficient from the expression of xt. All you need to do, you need to multiply the signal, periodic signal xt, with the corresponding the complex sinusoid with the corresponding harmonics of the spectral coefficient that we are willing to compute. For example, you are willing to compute the kth spectral coefficient, then you need to multiply xt with the conjugate of the uh, conjugate with the complex conjugate of the complex sinusoid with fundamental frequency kf naught, and take the integral over one period, so that will essentially provide you ck. And that is exactly something similar is happening here. You can see here your an, your complex sinusoid corresponds to an, it's not complex because sinusoid is cos 2 pi n ft. So basically you are multiplying xt with the sinusoid and taking the integral over the entire fundamental period. That's how you obtain the coefficient an. So with that, let us move to our next question. So so we have a periodic signal again, and this question has we have a periodic signal xt with fundamental period t naught, and its Fourier series is given as follows. So these are different spectral contents at k f naught frequencies for k integer, and ck are the corresponding coefficients. So it asks that what of the following is true according to Parseval theorem. So if we focus on the right hand side in all the cases, what is this term? Can someone help me out here, that what does the term on the left hand side in all these four options actually denotes for xt? Actually we have seen this on multiple occasions. Can someone help me out here, that what is the exactly this term on the left hand side for all this option represent? Okay, okay, let me answer it. This represent the power of xt, if you can see here, because we have already established the power for a periodic signal is given as the energy of that particular signal over one fundamental period, that is here 0 to t naught, and that being normalized by the period itself t naught. So that is the power of the periodic signal. So according to Parseval theorem, which one of the following holds? So basically we are willing to find the power of this periodic signal, and on the right hand side it gives us a feeling that it should be in terms of the spectral coefficients. So how do we exactly obtain that? So for that, let us do the calculation from here only. So it can be written as 1 over t naught. Okay, let me just not consider the constant parts as of now. Let's focus on the integral part first. So the integral runs from 0 to t naught, and absolute value of xt square is nothing but xt times the complex conjugate of it dt. So this is nothing but this, and this can be extended as 0 to t naught. We have to write k is equal to minus infinity to infinity ck e to the power j 2 pi f naught kt multiplied by, remember when you say x star of t, basically what will happen, we have two quantities here, one complex sinusoid, one is the kth coefficient, and the kth coefficients are also complex in general. So when you take the complex conjugate, you need to take complex conjugate of ck, and with that also the complex conjugate of the sinusoid here also. So x star t is have basically this expression. So let me use some index other than k so that they don't get mixed up. So let's use m here. So m runs from minus infinity to infinity. We have cm star e to the power minus j 2 pi f naught k t, and we have to compute the integral here. So inside there is a double summation, one is over k, another is over m. So let us bring the integration inside and take the summations outside. So what we'll essentially have is that k runs from minus infinity to infinity, and m runs from minus infinity to infinity. Cm star integral 0 to t naught e to the power j 2 pi f naught. Okay, this should be m here. This should be m. Okay, k minus m t dt. Okay, so let us take this to next page. Insert new slide. Okay, so what we have as of now, we are computing this integration and we have reached this part here. What we are having as of now, we are having k from minus infinity to infinity and m from minus infinity to infinity. We have ck cm star integration 0 to t naught e to the power j 2 pi k minus m t k minus m f naught t dt. Fine. Now let us closely focus on the case first when k not equal to m, because that is easier to handle. When k not equal to m, we will have k minus k sorry uh, we will have k minus m as some k dash, that is some integer. So that will make the integrand here as integration of 0 to t naught e to the power j 2 pi k dash f naught t dt for all k not equal to m. So you can see this is a sinusoid with frequency k dash f naught, right? So its period is t by k dash, where t is equal to 1 over f naught, right? And we are integrating it over integer multiple of its period, that is t naught is nothing but k dash time some this is period is t naught by k dash is some t1, and therefore t naught is actually an integer multiple of its period. So whenever we are integrating a complex sinusoid over integer multiple of its period, we are always going to get 0, right? For k not equal to m, this will always lead to 0. So what will at the end, we are left with only one summation, that is k is equal to minus infinity to infinity, or it may be m, doesn't matter, but one summation will only remain. And here we will have ck star. In that case, this integral here will become 0 when k is equal to m basically. So it will nothing but the trivial integration of dt from 0 to t naught. So essentially we will have k is equal to minus infinity to infinity absolute value of ck square, and we have t naught outside. Now we can bring the factor 1 over t naught here. So 1 over t naught 0 to t naught xt square dt turns out to be 1 over t naught times t naught sum over k is equal to minus infinity to infinity ck square. T naught cancels out. So we are left with the absolute value square of the spectral coefficients. So this is what Parseval theorem is, and this is the mathematical expression for that. But the intuition behind it is even more crucial. It says that power of a periodic signal can be actually written in terms of its spectral coefficients, and its value is actually immense. So you can see, first of all, the Fourier transform allows you to write the signal in terms of its different spectral components. And now Parseval theorems goes one step ahead, and it's saying that power can be represented in terms of the absolute value square, that is nothing but the power of the spectral coefficients. So that means if you know the different spectral coefficients of xt and you take their absolute value square and sum them all up, what you will end up getting is the power of the signal. And this also provides a crucial insights. You can see that which spectral coefficients contains what amount, what fraction of power of xt. For example, if I mean what I mean by that, if I have a Fourier series representation frequency domain of a signal like that, that has some very uh, high value at f, and lower values at 2f and 3f. Similarly, a higher value is minus f, lower at 2f and 3f, minus 2f and minus 3f. So what I can infer from that, that most of the power of the signal is confined in the frequency corresponds to the fundamental frequency f here, not in the harmonics. So the maximum power is confined in the f. Similarly, if it's the spectral coefficient corresponding to 3f is higher, then we can say the power of the signal is concentrated in the third harmonics of its fundamental frequency. So that's a very crucial insight that Parseval theorem gives you, that it first of all it allows you to compute the power of a periodic signal not only in terms of its spectral coefficients. More importantly, you can actually analyze that which of the spectral coefficients actually amounts to the most power for the periodic signal. That's a very important thing. So with that, let us move to our next problem here. So it says that Fourier series of a signal xt, it also says the fundamental frequency is given as 4 Hz. Now it asks for the coefficient in the Fourier series corresponding to the term e to the power j 16 pi t. Now you can just write the standard Fourier series representation we have already seen as k is equal to minus infinity to infinity ck e to the power j 2 pi k f naught t. So you just need to, what you do, you just replace 4 to f naught and see what you will obtain. So xt is basically given as k is equal to minus infinity to infinity ck e to the power j, f naught will replace by 4, so it will basically becomes 8 pi k t, right? Now just in the before slide we have seen that if we are willing to obtain the kth coefficient corresponding to the kth complex sinusoid, complex sinusoid at the kth harmonics of fundamental frequency, you can do it just by this formula 1 over t. You need to integrate the product of signal with the complex conjugate of the complex sinusoid you want to compute the coefficient for, it to the power minus j 2 pi k f naught t dt, and you need to integrate over any t naught sized interval where basically t naught is 1 over f naught. So it asks that what is the coefficient in the Fourier series corresponding to term e to the power j 16 pi t. So if you see, focus on this summation here, what you will obtain, let's pick only the positive one, not the negative ones. C naught corresponds to the frequency 0. Then we have C1 e to the power j 8 pi t. Then we have C2 e to the power j 16 pi t. So C2 is actually what we are looking for according to the question, because it asks to find the coefficient correspond to e to the power j 16 pi 2. So we have to find C2 here. So we can just plug the value of C2 here. C2 therefore 1 over T naught. So if frequency, fundamental frequency f naught is 4, your T is going to be 1 by 4. So here we are going to obtain 4. Integration range can be 0 to T naught, or integration range can be 0 to T naught, or it can be minus T naught by 2 up to minus T naught by 2. As long as the interval is T naught, it's fine, whichever interval we consider. So we'll have value of T naught as 1 over 4, so T naught by 2 is minus 1 by 8. Here we have 1 by 8. We have xt, we have e to the power minus j 2 pi k f naught is 4, k is equal to 2, another 2, so we have basically j 16 pi t dt. So this is our expression for the second coefficient, or the coefficient corresponds to the complex sinusoid with second harmonics of the fundamental frequency. Therefore the option 4 is the correct one, I guess. Yeah, option 4 is the correct one. So let us move to our next question. So it asks basically the Fourier transform for the signal xt is equal to 2 for t less than equal to 10 and 0 otherwise. So okay, so this is something of a pulse kind of signal in time domain. So let me draw the geometric representation for that. Just a moment. Okay, so xt is equal to 2 for absolute value of t less than equal to 10. So that means basically it has a width of 20. You have 10 here, you have minus 10 here, you have a value of 2, and this is what your xt is. So what is the Fourier transform of this signal that we need to find? So you can clearly say this is a aperidic signal. So we need to compute the Fourier signal expression. We have to apply the following formula here: xt to the power minus j 2 pi ft dt minus infinity to infinity. So what we have here, we have to integrate from minus 10 to 10, minus 10 to 10, because outside this interval it is 0. Xt picks a value of 2, so 2 can go outside. We have e to the power minus j 2 pi ft dt, integral of that. So that will amount to 2 over minus j 2 pi f. Okay, and here we'll have e to the power minus j 2 pi f t at a value of minus 10 and 10 here. So we'll obtain 2 over 2 here cancels out, 1 over minus j pi f. We have e to the power minus j 2 pi, it's 20 pi f minus e to the power j 20 pi f. So this here minus j pi f, so this actually we can use this formula that e to the power uh, j omega t minus e to the power minus j omega t divided by 2j is actually sine of omega t. So we just replace it here. So what we will obtain is minus 2j sine 20 pi f. Am I correct here? Yes, correct only. So this minus minus and j will cancel, so we'll leave left with 2 sine 20 pi f divided by pi f. So this kind of pulse in a time domain have its corresponding Fourier transform given as this 2 sine 20 pi f by pi f. So the answer stops here, that is the fourth one, but there is one more point I would like to emphasize here, which is this function have a particular name for that. So it's basically can be written as 20, not 20 or okay, 40 times uh, sine 20 pi f by 20 pi f. So this is written as 40 sinc 20 f. So I would ask you to forget about the constant part, but most focus about the sinc one. So this is a special function, sinc of x. Sinc function is given as sine pi x divided by pi x. So these functions of course you have encountered in the course. So basically whenever you have a pulse in time domain, something like this aperidic pulse, the corresponding Fourier transform is going to be sinc function. So sinc function has striking similarity with the sine function itself. Only difference is that its amplitude also goes down. The amplitude of sinc function also goes down with the x. So apart from that, it is quite close to sine function, and it has one more property that sine cx sinc, let me introduce a new slide here. So sinc function has this nice, nice and unique property that sinc of x is equal to 1 for x is equal to 0, and sinc of x is equal to 0 when x is equal to some k pi, where k is some integer. So this is the property of sinc function. So we move to the next question, which says about the Dirac delta function. So Dirac delta function, practically exact Dirac delta doesn't really exist, but it's more of, you can consider as a mathematical tool. It really simplifies its analysis, and it has this weird property, I would say. So this is something you call Dirac delta intuitively. This is the geometry representation of Dirac delta. So it has three properties. First of all, Dirac delta is at any value t is 0 for t not equal to 0. This is the first one. Second property is holds is Dirac delta of 0. Okay, this is not defined, So Dirac delta at t is equal to 0 is not defined. And third one is integral of Dirac delta over the entire interval is turns out to be 1. So among these answers, the third one is the really correct one we are looking for. But Dirac delta, how can you visualize in terms of other signal? So for that, I am sure you have seen in the course, but I am just trying to reiterate here. You just consider a pulse here centered at 0. This pulse has, you just focus on this property, that it has the amplitude of t, whereas its width is uh, sorry, it has a, yeah, so its width is 1 over t. So how do we ensure? Basically it's from minus sorry, so this one you have 1 over 2t minus, and here we have 1 over 2t. So basically the width becomes t and the height becomes capital T. So you can see when you basically consider the area of the pulse, so that turns out to be t into 1 over t 1, right? So now you consider that t to increase, okay, you push t upwards as much as possible. So what will happen? The amplitude will increase. So let's say this is a function p t, we are calling it pt. So you increase t, what will happen? Your amplitude will keeps on increasing, but your this width here, this 1 over t will keep on shrinking. So the next step may be something like this, next step something like this, and you increase the amplitude even more, your pulse would even get shrinker. So at the extreme case, that is limit t tends to infinity, this p of t which is denote the pulse. So then at this limiting case, it mimics actually the Dirac delta function, because in that case your t will be very close to infinite, your width is going to be infinitesimally small, but the area under this pulse is going to be 1. So that is what the property Dirac delta satisfies, and this is how you, so Dirac delta is more of a mathematical tool, but from a practical viewpoint also you can see how in the limiting case when t tends to infinity, this pulse here will start mimicking the Dirac delta. So about Dirac delta you need to remember these three fundamental properties. This is more of a mathematical tool that is really helpful for our analysis. We'll see from the next session onwards. We have immense use of that. So now we have a signal mt is a question. So just a minute. Yeah, so mt has this Fourier transform um, mf. So now what you do, you multiply mt with sine 2 pi fct, and now you ask me what is the Fourier transform of this composite signal. Now one clever way to do this, we can use this property here, sine omega t is e to the power j omega t minus e to the power minus j omega t divided by 2j. I am going to apply this here. So what I will obtain? I will obtain mt times e to the power j 2 pi fct. I have common term here 1 over 2j. I have this, and then I have this mt e to the power j minus 2 pi fct. So I have to compute the Fourier transform of these two separately. So remember, in time domain we are multiplying with complex sinusoid, right? Let's say time domain, and on the other hand side we have frequency domain, right? So the manipulate we have seen in the, you have seen in the course also, that when in time domain you multiply a signal, multiply a signal with uh, complex sinusoid of frequency f naught, what will happen to the frequency domain representation of it? It would just get shifted by frequency f naught. So that is, I would say, like a cool thing. When you move from the time domain representation to frequency domain representation, you are multiplying mt here with sine 2 pi fct. So I am using this identity here, writing this in terms of a complex sinusoid, two complex sinusoid, e to the power j omega t and e to the power minus j omega t. So I end up with these two here, whose Fourier transform I need to compute. But what the property already said, in time domain you multiply the signal with a complex sinusoid, which is this, of a frequency fct. Here it's minus fct. So that basically lead to the frequency domain. You just shift the frequency, you just shift the frequency domain representation by a frequency f naught. Now how that will happen, so let me just show for a moment. So let's say we have xt, right, and you multiply it e to the power j 2 pi f t, right. So now xf, what will happen now for this particular x dash f, let's call it x dash t. So the corresponding Fourier transform will become, what will become, minus infinity to infinity x dash t, which is xt e to the power j 2 pi f t, let's say fct, this will multiply with fc, and e to the power minus j 2 pi f t dt, correct. And this is nothing but minus infinity to infinity xt e to the power j 2 pi, take the minus here, f minus fc t dt, and this you can see is nothing but x f minus fc. So when you multiply in the time domain by a complex sinusoid, what we end up doing, the frequency domain representation of the altered signal x dash is nothing but a shifted version of the original signal by a frequency fc, which is the frequency of the sinusoid. So similarly you can just see from here, I'll introduce a slide here and explain. So we are having as of now 1 over 2j mt e to the power j 2 pi fct minus mt e to the power j 2 pi fct, minus here. So if I take Fourier transform of this individually, we can take, so this will lead to 1 over 2j, I'll have m f minus fc, and here I will have m f plus fc. Now in the numerator it's 1, so that can be written as minus j square. J square is minus 1, minus j square is 1. Now we have 2j below, we cancel out, so it will happen that f minus fc minus m f plus fc, and let's see which of the answer matches. The coefficient is minus j by 2. So coefficient is minus j by 2, which of the cases, and it should be negative for f minus fc. So minus j by 2 m minus fc. Okay, now this one is the correct answer, right? Or m plus fc should have plus, so plus fc, yeah, this one is the correct answer here. So with that I would like, so if you guys have any question till this point, you can, it's a good time to ask. I hope this is helpful for you to solve in the assignment problems you are given. If you don't have any questions, then we can conclude the session. You can ask me like any question, any doubt you have, or anything you found to be wrong in explaining or not very clear to you. I'll explain again. Please don't hesitate to ask. Okay, if you don't have any question, then I'm concluding the session. We'll meet uh, again next Saturday, the same time, for our next session. Thank you all for being with me for the entire session. I'm concluding the session. Thank you all.